Have you ever just stopped and realized that pretty much everything is moving all the time? I mean, from the tiniest atoms just kind of vibrating to entire galaxies hurtling through the cosmos, nothing is ever really, truly still. And the rules that explain all of that movement, well, that's physics. So let's dive into how it all works.
We've all been there, right? That feeling on an amusement park ride, getting whipped around in circles, feeling like you're going to get launched into orbit. So what is it? What actually pins you to your seat? The answer to that and to so much more is physics. It's the instruction manual for the world we experience every single day.
All right, so before we can get into the why things move, we first need to get on the same page about how to talk about it. In physics, words are super precise. Getting the language right is, believe it or not, the first big step to unlocking the whole thing.
So we all talk about speed, but in physics, the word you really need to know is velocity. And the difference is so simple, but it is absolutely crucial. Velocity is just speed with a direction. 60 miles an hour, that's a speed. But 60 miles an hour north, now that's a velocity. And that little detail, that changes everything.
And what about acceleration? We think of it as just hitting the gas, right? Speeding up. But in physics, it's any change in your velocity. And because velocity includes direction, that means slowing down is a form of acceleration. And get this, even just turning a corner at a perfectly steady speed is acceleration, because your direction is changing. It's a way bigger idea than most of us realize.
Just think about an F1 car. That thing is a masterclass in acceleration. It's not just about blasting down the straightaway. It's about slamming on the brakes into a corner and then exploding out of it. It is constantly changing its velocity, both its speed and its direction. That's the whole game right there.
So how do scientists keep track of all this? Well, they turn that motion into pictures, into data. By plotting where something is over a period of time, they create this visual fingerprint of its journey. A graph like this could show you the motion of, a tortoise or a top-fuel dragster. And from these simple lines, we can figure out its exact velocity and acceleration. It's how we turn the messy real world into clean, predictable math.
Okay, now that we've got the language down, we can get to the really good stuff. The 3 fundamental rules that control all motion everywhere in the universe. We're talking about Isaac Newton's 3 laws of motion. He figured this out over 300 years ago, and they're just as true today.
First up, Newton's first law. You can think of it as the law of inertia, or maybe even the universe's default setting. Basically, things just want to keep doing what they're already doing. If an object is sitting still, it's going to stay still. If it's moving, it's going to keep on moving in a straight line at the same speed pretty much forever, unless something gets in its way.
And if you want a perfect, beautiful example of this, look no further than the Voyager 1 spacecraft. It was launched way back in 1977. It fired its engines for a bit, and then they just shut off. For over 40 years, it has just been coasting. Through the near-perfect vacuum of space, with almost nothing to stop it, it just keeps going. That is Newton's first law in action, on a cosmic scale.
So the first law tells you what happens when there's no force. Newton's second law tells you what happens when there is a force. And this little formula, F equals ma, it's arguably the most important equation in all of classical physics. It's the recipe that tells you exactly how much push or force you need to make something with a certain mass accelerate. It's that simple. More force, more acceleration. More mass, and you're going to need more force to get the same acceleration.
And this classic experiment shows it perfectly. See the hanging weight? That's providing the force. It's pulling the cart. If you add more weight to the hanger, you've increased the force, and surprise, surprise, the cart accelerates faster. But if you add more mass to the cart itself, that same force doesn't push it as hard. It has less acceleration. It's a perfect visual of F equals ma.
And finally, we have the third law, probably the most famous one. For every action, there's an equal and opposite reaction. What it really means is that forces never, ever show up alone. They always come in pairs. You push on a wall, guess what? The wall pushes back on you with the exact same force. Always.
And there's no better place to see this law in action than in the total weightlessness of space. Imagine an astronaut just floating out there. How do they move? There's no ground to push off of, no air to swim through. The answer is Newton's third law. To move forward, she has to throw something, anything, backward. That action, throwing the tank,
creates an equal and opposite reaction, which is the force that pushes her forward. That's it. That's the core idea behind every rocket ever built.
So, Newton's 3 laws. That's the foundation. That's the bedrock. But to really become a master of motion, physicists use a couple of powerful concepts that feel like, well, they feel like cheat codes. We're talking about the conservation of energy and the conservation of momentum.
First up, energy. In mechanics, we mostly think about it in 2 flavors. You've got kinetic energy, which is the energy something has just because it's moving. The faster it goes, the more kinetic energy it has. And then you have potential energy. That's stored energy. It's the energy something has because of its position. Like, being held up high, just waiting to be released.
A water slide is the perfect place to see these two play together. At the very top, before you go, you're just loaded with potential energy because of your height. Then, as you slide down, you lose that height, and all that stored potential energy transforms into kinetic energy, the energy of pure motion. The law of conservation of energy says that total energy is never lost. It just changes its outfit.
Our second cheat code is momentum. You can just think of it as an object's mass in motion. It's oomph, and here is the secret. Momentum is always conserved. In any collision, like between these 2 carts here, the total amount of momentum you have before they crash is the exact same amount you have after they crash. It just gets transferred between the objects. Nothing is ever lost, and because of that, we can predict exactly what will happen in any collision.
So, there we have it. We've got our complete physics toolkit, a precise language to describe motion, 3 fundamental laws to predict it, and 2 powerful conservation principles to analyze it. So let's bring it all home and see how this stuff explains the world all around us. So here's the big picture, the main takeaway. We've basically built a 3-step way to understand motion. First, we learned how to describe it precisely with words like velocity and acceleration. Second, we used Newton's incredible laws to predict how forces are going to affect that motion. And third, we used those powerful conservation laws, those cheat codes, to analyze whole systems, from a simple car crash to that crazy amusement park ride from the beginning.
And the way we use these ideas, it's just staggering. I mean, the very same laws that let you figure out the path of a thrown baseball are the exact same laws NASA uses to plot a course for a spacecraft across millions of miles of empty space. And the principles of force and energy, they're at the heart of medical devices that can save lives with unbelievable precision.
But really, you don't have to look to outer space or inside a hospital to see physics at work. Just look down. The simple act of walking is this beautiful, complicated dance of forces. Your foot pushes back on the ground. That's the action. And the force of friction from the ground pushes you forward. That's the reaction. It is Newton's 3rd law happening with every single step you take.
So, we've built this incredible way of understanding motion, from our own bodies all the way out to the stars. Newton's laws are powerful, they're predictive, but they're not the whole story. What happens when things get really, really tiny, down at the level of an atom? Or when things get insanely fast, like close to the speed of light? Well, that's where things get weird. That's where classical physics starts to break down and a whole new set of rules takes over. But that is a story for another explainer.